In this video, we're going to talk about a big topic, namely inverse functions. And before we actually get into inverse functions, we need to make sure that we're all good and understand what it means to do a composition of two functions. So if you have two functions, f of x equals x squared plus 3x, g of x equals 2x plus 1, if you're asked to find something like this, remember now, even though we use parentheses to mean multiplication sometimes, in this context, this means f of g of 2. It's not multiplication. What you're doing is you're running the number 2 through two functions here. And so, by the way, this can also be known as, sometimes you see this written as f, and they put a little circle of g of 2. That means the same thing. It's just kind of old school notation. I don't really care for that. So anyhow, what makes sense is to start on the inside. Let's find out what g of 2 is. If I put 2 in for x, 2 times 2 plus 1 gives me 5. And so that's what this simplifies to. So then we want to just find f of 5, plug 5 into f of x. 5 squared plus 3 times 5, 25 plus 15 gives me 40. Remember, you can do a composition both ways. So if I've reversed it and did g of f of 2, now I should be plugging 2 into f of x first. That's going to give me 2 squared. 4 plus 6 is 10. And then find g of 10. 2 times 10 plus 1 gives me 21. And just one thing to point out, because I'm going to bring this up when we talk about inverse functions, is it's the same two functions, same number. We reversed the order of the composition and we did not get the same numbers, right? Not equal. And that's, you'd probably expect that to be the case most of the time because of the order. It depends on the order we plug the number in, right? So another thing you could be asked to do, which will kind of confirm why we're getting two different answers here, is let's see what happens if you do f of g of x in general. So I want to, same thing, I want to start with g of x, which g of x was the function that was 2x plus 1. So I'm just going to replace that with 2x plus 1. And now I have to evaluate f of 2x plus 1. We can't see f of x. I'll write it up above here. F of x is x squared plus 3x. So in the same way you did, like, for example, f of 5, where you plugged 5 in for both x's, f of 2x plus 1 means I'm going to plug that in for both x's. So it's going to be 2x plus 1 squared plus 3 times 2x plus 1. You could probably do more algebra to rewrite that, but let's not worry about that right now. G of f of x means I want to take g of the entire function f of x, which was x squared plus 3x. Reminder here, g of x was 2x plus 1. So just like we did here, I'm going to plug x squared plus 3x in for that x. That's the input. So it's going to equal 2 times x squared plus 3x plus 1. And now you can kind of see why, you know, we weren't expecting to get the same number, because these are completely different functions, right? Depending on what order we do the composition. Sometimes, however, if we have two special functions, let's see what happens here. F of x is 4x plus 1 over 3. G of x is 3x minus 1, all divided by 4. F of g of 7 means I'm going to plug 7 into g. Let's just do that in our head. 3 times 7 is 21, minus 1 is 20. Divided by 4 gives me 5. So then I would be doing f of 5. 4 times 5 is 20, plus 1 is 21, divided by 3 gives me 7. Now we'll reverse the order, and we saw that we usually don't expect to get the same answer, but let's see what happens. F of 7, 4 times 7, 28 plus 1 is 29 thirds. And then I got to take 29 thirds now and plug that in for g. I'm going to write this out so we see it. It's 3 times 29 thirds minus 1 divided by 4. 3 times 29/3 is just 29, minus 1 is 28 over 4, gives me an answer of 7. So there's actually two interesting things going on here, I think. Number one, of course, is unlike the first problem, and we normally wouldn't expect this, these came out to be the same number, even though I did the composition both ways. But another interesting thing is in both cases, I got the number I started with, right? I started with 7 and I ended up with 7. So that's another interesting thing. Now, maybe you could say, well, maybe it was just this number 7, right? Maybe that is something special about 7 as why that happened. Well, let's confirm this. Let's see how this works for any x value, right? F of g of x. If what we're seeing up here is true, what we're expecting to get back, we're expecting to get back our original input, which was x. I'm going to put a question mark. Well, let's see. G of x is the function 3x minus 1 divided by 4. So I have to do f of that. I guess I don't have f of x. Let me rewrite that. F is 4x plus 1 over 3. So that I would plug this in for x. So 4 times 3x minus 1 over 4 plus 1, and divide the whole thing by 3. Well, let's see what happens here. The 4s are going to cancel. Once they cancel, this could just drop down. The minus 1 and the positive 1 cancel. And once those cancel, 3x divided by 3 just leaves me with x, which is what we were kind of thinking might happen. Let's see if it happens the other way. G of f of x means I want to take g of 4x plus 1 over 3. G of x was the function 3x minus 1 divided by 4. Oh, I already wrote that there. So we're going to plug this in for x. So that's going to be 3 times 4x plus 1 over 3 minus 1 divided by 4. And sure enough, 3's cancel, 1's cancel, then the 4's cancel, leaving me with just x. So this kind of confirms what we saw happening there is going to work for any number, right? Any input x, I'm always going to get back the same thing I started with, and it's going to happen either way I do the composition. So there's something special about this, and one way to illustrate it, if many of you are probably familiar with the idea of a function machine, if you think of g of x and f of x as machines that take inputs and then, you know, do some operations on it and then turn it into a different number. F of g of 7, we did that up here, right? The first thing we did is we plugged in 7 as our input for g of x, and what came out was actually a 5. If you plug that into g of x. But then we saw when we plugged 5 into f of x, it got us right back to the 7. So in a sense, right, g of x changed the number, did some operations, changed the number 7, and f of x undid those changes to get back to our original number. So that's the way I like to think of these. F of x and g of x undo each other's operations, giving back the original input. And whenever this happens, we say that f of x and g of x are inverses of each other. So we could say f of x is the inverse of g of x, or g of x is the inverse of f of x. Either way, I'm going to go use g of x. And the way we denote that, this is one of the worst ways to denote an inverse function. If it were up to me and I wanted to say that g of x is the inverse of f, what I would have done is put like a little I up here maybe to stand for inverse. But I didn't make up this notation, somebody else did. Someone decided to make that -1 of x. Now that's very, very confusing, right? Because in math, whenever you see something to the -1 power, like x to the -1, you're supposed to do 1 over x. but this is not this is not 1 over f of x. We don't mean that. In this context, this means f inverse of x is how you would read that. Let me move that up so you can see that. F inverse of x is what this notation means. It's not 1 over f of x. Okay. So the next thing to work on is how do you find an inverse if you're given a function? You should be able to find the inverse. So I want to find the inverse for f of x equals 7x cubed minus 5, the whole thing divided by 2. It's to find the inverse. A lot of students and teachers think of it as a two-step process, like a recipe you follow. Most teachers teach this. And first you switch x and y, and then you solve for y. I actually do it backwards. I'm going to put most books and perhaps teachers teach that to find the inverse. For me, I actually reverse it. What I first do is solve for x, and then I switch x and y. So I'm going to go with my method. I've been teaching a long time, and there's a reason why I don't follow the book's typical method, which I will tell you about soon. So I'm always going to solve for x first. Remember that f of x is just a fancy name for y. So if I was going to solve this for x, what I would first do is multiply both sides by 2. I would add 5 to both sides. I would divide by 7 and then take the cube root. Well, I'm going to move the x cubed over to this side now. So I'm going to have 2y plus 5 over 7, and then finally take the cube root. So I've solved it for x, and then the last step is to then switch x and y. And once you get that solved for y, this is the inverse function. So I'm just going to say that equals f inverse of x, and I'm just going to highlight that part. Okay, so again, I'm just solve for x. And then the last step from here to here was switch x and y. Switch x and y. All right, let's try one more. If you're got that and you want to practice this one, you should pause the video and see if you can get the inverse for this function. Assuming you did that now, we'll just jump right into it. So f of x is y. To undo a 5th root, what you would want to do is raise both sides to the 5th power. So the left side is going to be y to the 5th. Then to get x by itself, I'm going to want to subtract 1 and then divide by 6. So x would be y to the 5th minus 1 divided by 6. Then I will switch x and y. And once I've done that, that is my inverse function. So not too bad. Before we go any further with inverse functions, there's something special that you should know about what happens when you graph a function and its inverse on the same set of axes. So I'm going to use as my example, f of x equals x cubed, and the inverse of that, which, okay, let's just think about this just from an intuitive level. If you cube a number, plug a number here into f of x and cube it, what function would you plug that number in to get back to your original number? Well, it would make sense. You should plug it into the cube root of x function, right? That's the inverse of cubing something. So let's graph these together. F of x equals x cubed is one of our important graphs. It's a good graph to know. It's a base graph, a parent graph. Remember, it passes through 1, 1. If x is 2, 2 cubed is 8. It passes through -1, -1. and then -2 cubed is -8. And it has that look, remember, it gets kind of flat at the origin and curves up like this. So here's y equals x cubed, f of x. Now to find the inverse, most people don't know what the graph of cube root of x looks like. It's not that important of a graph to know. But here's an interesting way to think about the graph. Remember that one of the processes for finding the inverse is at some point we switch x and y. And so graphically, it's the same way. If the point 2,8 is on the graph of f of x, which point will be on the graph of f inverse? It's going to be 8,2. 8,2, which might be like over here somewhere. Which makes sense. If you plug in 8, the cube root of 8 is 2. 1, 1, if you flip that, you still get 1, 1. So, and that makes sense. The cube root of 1 is 1, as is the cube root of 0, as is the cube root of -1. But -2, that should be -8. If you reverse those x and y values, you get -8, -2. And if you kind of interpolate in between, what you'll see is the graph of cube root of x actually looks something like this. This is f inverse. And what happens is when you graph a function, any function in its inverse, and you switch the x and y values, what you'll always see is there's a symmetry that happens. I could draw a line right through here, a diagonal line, going through the origin, 1, 1. That line is y equals x. And you could think of the graph of the inverse, if I just took f of x and folded it around the line y equals x, each part, even this part, if I folded it, this part, if I folded it, this part, you would get the graph of f inverse. And so this is always true. The graphs of f of x and f inverse of x are always symmetrical about the line y equals x. And that's, going forward for things we're going to do later on, we're going to take advantage of that fact to graph certain functions, especially when we get to log functions and exponential functions. So just a simple example, I could ask you on a test, if I gave you kind of a made up function that's made up of like maybe a piecewise function, maybe part of a parabola and then a straight line, and ask you to sketch the inverse function. As we know, the x and y values would just get reversed. So instead of passing through -3, 0, it's going to pass through 0, -3. 0, 4 on my inverse function is going to be 4, 0. And 2, 5 is going to turn into 5, 2. Maybe something like that. And what might help too, we know it's going to be symmetrical about the line y equals x. So if you kind of just imagine that line drawn through here. Because the other thing I'll be checking for is that the curvature looks right. If you folded this graph around the line y equals x, it's not going to look like this, right? So if you drew it like this, that would be incorrect. I forgot to label this point. That's 0, -4. If you folded this around the line y equals x, it's going to curve like this and then go up to this point like that. So it should look like it's symmetrical. I'm not only checking that you've reversed the x and y coordinates, but I'm also looking for the shape, that it should look symmetrical about the line y equals x. Okay. Back to inverses. I don't know about you, but I like to think math is supposed to be good for something here, right? We're supposed to be not learning this just for fun, but it ought to be able to help us answer a question. And there is a nice use for an inverse function. There's plenty of more uses, but this is one that that is very pertinent to things we're doing right now in class. We've talked a lot about finding the domain of a function, which is the x values. But to find the range of a function, which is essentially all of your y values that your function takes on, that's a lot harder, generally speaking. I'm going to make a video soon after this one telling you lots of strategies for how to find the range of a function, and this will be one of them. So how we're going to do that, if we think about f of x and f inverse of x. And now we know that we switch the x and y values. So if I was interested in the y values, I'm sorry, I put it in the wrong place. If I was interested in the y values for f of x, which I am, remember we switch the x and y values, so that would correspond to the x values of f inverse of x, right? These would be the same. In other words, the range of f of x will be basically the same as the domain of f inverse of x. Okay, and we'll tell you why I say basically the same here in a second. So the strategy would be, if I find the inverse of this function, I could think about the domain of that, and I would know that those x values would correspond to the y values of f of x. Okay, so let's go ahead and find the inverse. So I'm going to take this function, f of x is really y, so let's move this down here. Y is equal to 1 over x minus 2 plus 3. I want to solve for x. So I'm going to subtract the 3 over. Now, my favorite way to do the algebra from here, yes, you can multiply both sides by x minus 2. But my favorite way to solve when I get in a situation like this is if I flip the right side, in other words, take the reciprocal, because that's just going to give me x minus 2 over 1, which is just x minus 2. Remember, for an equation, whatever you do to one side, you have to do the same thing to the other side. So I'm going to make this 1 over y minus 3. So I'm taking the reciprocal of both sides. I just think it makes the math a little bit easier. Because then to solve for x, all I have to do is add over a 2. So I get x is equal to 1 over y minus 3 plus 2, which means, let's move this up here. Last step in finding the inverse is to switch x and y. So y is equal to 1 over x minus 3 plus 2, which I know is my inverse function. Okay, so I've got my inverse right here. So then I could take advantage of this idea. What is the domain of this inverse function? And hopefully you can see the only thing I have to worry about is I can't divide by 0. So the domain of f of x is x cannot be equal to 3. I could write that in interval notation, which I might do when I get to the range, but this is what I mean by they're not exactly the same. So therefore, what I could say is the range, I'm sorry, the domain of, this should have been the domain of f inverse of x, right? The range of f of x, which is what I want, it's not that x is equal to 3, it means that y could not be 3. Right? That's why I say they're not exactly equal, because domain you're talking about x values, range you're talking about y values. If you put it in interval notation, then I suppose they would look the same, because all the numbers that are not or equal to 3 would be from -infinity to 3, and then from 3 to infinity. Either way. So let's try that one more time. Let's see if we can find the range for this function now that we know what we're going to do here. Oh, by the way, let me come back to this one, because this is a good chance right here for me to explain why I solve for the inverse a little bit differently. I said earlier that I always solve for x first and then switch x and y. And it's for a problem like this that I started doing that. Because let's say you didn't quite get all the way to the inverse, but you got to right here. In other words, you solved it for x. If you were asked to find the range of f of x, which is essentially what y can and can't be, hopefully you can see right here, it's staring you in the face, right? I can see right here that y cannot be equal to 3, which is exactly right what we got there. So if you solve for x first, you don't even have to finish it off. You don't even have to actually go and solve for the inverse. You can already tell from here what y can and can't be. Okay, or you can go all the way to the inverse, find the domain of the inverse, and then argue that the range would just be the same, but with your y values. Either way. Okay, so let's try that here. I'm going to start by solving this for x. This is equal to y. Let me just rewrite this. So I have y is equal to 6x plus 1 over 3x minus 5. Here I don't see any advantage to flipping this, so I'm going to multiply both sides by 3x minus 5. Here it's going to cancel. Here I'm going to distribute, so I'm going to have 3xy minus 5y equals 6x plus 1. On a problem like this, I notice a lot of times I get a lot of questions, people get stuck here. The goal is to solve for x, and you have x in 2 spots. So what that means is we ought to get these 2 terms together and get everybody else on the other side. The easiest way to do that, I would just say, is what if we just change places with these 2 terms, right? In other words, subtract the 6x over here and add the 5y over to the right side. So 3xy minus 6x equals 5y plus 1. Why do I want them on the same side? Because then I can factor out an x. Notice you can, your normal factoring instincts, you can take out a 3x, but our goal is to solve just for x, so you don't need to take out the 3. And then if I solve for x, I get 5y plus 1 over 3y minus 6. Now, I'm going to take this chance now to it just says find the range. It never said find the inverse. I could take the additional step of switching x and y and calling that the inverse and then finding the domain. But if you just look at that, I bet you can already tell me what y can't be, right? Because you have a fraction and we can see that 3y minus 6 cannot be equal to 0, which means y can not be equal to 2. And that would be my range, right? Which in interval notation is from negative infinity to 2, union 2 to infinity. This would be my range. One last thing with inverses. I get a lot of questions on these types of problems too, where you're given a function and you're asked to find the inverse at a number. Like I want to find f inverse of 7 for this function. So the logical thing to do would be, okay, if they want to find the inverse of 7, I should start by trying to find the inverse here. But what you'll notice is I can try to solve for x, and it's going to be difficult here, right? I don't think you could solve this for x very easily. Right? Even if you subtract the 2 over, what are you going to do from here? I mean, if you factor out an x, you still don't have a really good way to solve for x, right? If you divide by x squared plus 4, you haven't solved for x because you still have x on one side. So the point here is I'm going to stop short of saying it's impossible to solve for x, but it certainly is going to be very difficult to find f inverse of x, right? So what am I going to do? If I can't find f inverse of x, how am I going to find f inverse of 7? So the answer is this. You don't actually have to find the inverse to answer this question, because you have to remember that because of the relationship between f of x and f inverse, and the x and y coordinates are switched and reversed, asking what f inverse of 7 is the equivalent to asking f of what gives me 7, right? This and this means the same thing. So another way to approach the problem is to say, what would I plug in for x here to give me 7? In other words, f of what, if I were to take some number, cube it, plus 4 times that same number, plus 2, what number would I plug in and get me 7? I mean, that's the equivalent to just trying to solve, right? X cubed plus 4x plus 2 equals 7. It's the equivalent to trying to solve for x, but you're going to run into the same problem. That's not easy to solve for x. So what do I do then? When this happens, don't try to solve it algebraically. Instead, and I know this is not something your math teachers usually allow, you're just going to guess and check. Or the fancy word, math word you'll see in some textbooks is they will say by inspection. In other words, they're just guessing. If you look at this, what number would you plug in for X here and get 7 as your output? Don't think really hard. It's not going to be something complicated. Can you see that if you plugged in 1 for X, you're going to get 7? So by inspection, we see that f of 1 gives me 7. Therefore, f inverse of 7, which was my original problem, must be equal to 1. See, it's possible to answer this question without actually finding the inverse. And just so you can see one more, now that you see how those kind of play out, let's try this one. F of x equals this crazy function here, and they're asking for f inverse of 1. Hopefully, you're not going to attempt to try to find the inverse of that, right? It's going to be very difficult. So just think of it this way, right? Finding f inverse of 1 equals something is the equivalent to saying f of what would give me 1. So in other words, what would you plug in for x here so that this whole thing came out to be equal to 1? Don't think too hard. Do you see that it's just going to be 0? If I plug in 0, all of those terms are 0, and I'm just going to end up with 1. So because f of 0 is equal to 1, that means that f inverse of 1 has to be equal to 0. They write these problems very carefully so that, obviously you could say, well, what if it's a crazy number that gives me this thing, right? Like, a fraction or something really big. They always write them so it's usually a very simple number that you would plug in to get this output here. So don't get too concerned with that. All right, hopefully this helps give you a better understanding of inverse functions, how to find them, how the graphs are symmetrical with f of x. And we're going to be working with inverse functions a lot in calculus.